Hello everyone, welcome to the second to last day of solving Advent of Code. Today is day 11 and that's what we will be doing, solving day 11 of Advent of Code. Hey folks, hey Roger, Paramesh, Ivan, how's everyone doing today? Well, let me actually adjust this. Alright, brilliant. Let's get straight into it. Day 11 is a graph problem. You are given an input like this, where on the left, on each line on the left, you have a, what do they call it? A device. And to the right of the colon, you have a list of other devices. Oh, I can't believe that this is ordered. No, it's not. All right. Sorry, for a second there I thought the input came in a special format. Right, so you have devices and the outputs they map to. And the idea is that if you follow the devices and their mappings, you can create paths through the different devices. So you're essentially creating connections between devices. And the connections are directed. So you can't go back, you can only go in the direction that the input gives you. So from A, you can go to U, but not the other way around. And then the question for part 1 is, if I'm not mistaken exactly, in how many different ways can you go from U to out? How many different paths are there? So let's solve this. Let's start by grabbing the input file. Now, apologies in advance, my voice is a bit not great. Oh, I already had my input. All right, so there's that, and now we take a look at the code. Solution.py. First things first, as per usual, let's parse our input. We're going to open our file path in read mode, and then we're going to go through the lines, and we're going to build a dictionary with the connections. So for each line in my file, I'm going to partition the line to grab the source and the targets. So I'm going to partition it. So this finds the colon and the space and gives me a source on the left and the targets as a string on the right. And then what I'll do is I'll say that in the dictionary connections, the source maps to the set with all the targets. And then I return my connections. And this is already more than half of part 1 solved. Now, I'm going to take my connections from my input. And then I'll do print part 1 of connections. So now what is the function part 1? This function, in here I need to count in how many ways I can go from U to out. So really what I can do is, yeah, let's make it here. Sorry, I was thinking for a second. So I'll define a function count paths that starts from a given position and looks for paths to a given position. And this is going to be a recursive function. If the point I'm starting from already matches the point I want to get to, then there's only one path to go from the starting point to the end point. Otherwise, what I need to do is I need to take a look at the starting point, take a look at its neighbors, and then count the paths from the neighbors to the target. So that's count paths from the neighbor to the given target for each neighbor in the connections of my starting from the connections of my starting point. And part 1 just returns the count paths from U to out. And if I run this, I get an error because what am I doing wrong? Connections. Where's the problem? Line 25. My bad, sorry. This is supposed to be my file path, not connections. Alright. And as per usual, Paramesh in the chat figuring out what my problem is before I do. Was the answer 670? Yes, it was. Okay, so part 1 is solved. Part 1 is solved already. I just need to count the paths from this given position to this given position. And this does depth first search, because I'm going deep into the connections before checking different connections. Alright, any questions about this? Because if you understand this solution, then you're going to understand the part 2 solution as well, because it's very similar. Alright, in that case, let's keep going. Because for part 2, let me open the Advent of Code site. Part 2 is similar. I still have connections given in this format, but this time I want to start at SVR, which I think is supposed to be server, and I want to go to out, but I only want to consider paths that go through FFT or DAC. Sorry, not or. Through both. So I have to find all paths from SVR to out that visit both DAC and FFT. And this is surprisingly simple to solve. I'm going to copy this part 1 and paste. I'm going to call this part 2. And now all I'm doing is I'm counting the paths in the same way, but when I reach the end, I only want to consider paths that visited DAC and FFT. So I'll return visited DAC and visited FFT. So what this essentially says is that a path is only valid if it visited both. Now, how do I keep track of these variables? Well, when you start counting the paths from SVR to out, you know that you haven't visited neither. You haven't visited DAC and you haven't visited FFT. So what you can do is you create 2 arguments in your function count paths that keep track of whether you already visited these 2 important nodes or not. And now it's just a matter of keeping them updated. In the beginning they start as false, but when you call the function count paths recursively, you'll want to update this information based on whether you're just at the point that is one of these 2. So you'll want to update this to say if you either already visited it or your neighbor is DAC or DAC. Right? So if you're about to enter the neighbor DAC, then you know that you've visited it. And you can do a similar thing for FFT. Let me just make this, split this across a couple of lines, and then it's visited FFT or neighbor is FFT. Now, theoretically, this is already enough to solve your problem. You can run this piece of code. Let's run it. Wrong tab. So theoretically the code is correct, and the code runs and produces the correct result. The problem is it's very, very slow. I don't know how long I would need to leave it here to actually compute the correct result. But what's the problem here? Why is this code very slow? The reason is really just branching. We're branching out and merging or converging on paths down the graph, and we're just recounting every single path every single time. I wish Excalibur opened So the idea is very simple. You start at SVR, and this isn't necessarily true for these exact vertices, but the idea holds. Suppose, actually not out, but something else. So SVR can go to BBB and AAA, and they both go here. Your function is going to try to count the paths on both, right? It's going to go through BBB and then it's going to go through AAA. And when it goes through BBB, it's going through this path as well. And the function count paths will count the paths from this node onwards, whatever is there. So when you go through AAA, from SVR to AAA, and you check this node again, what's happening now is that you're recomputing this whole thing again, but you don't need it. You don't need to recompute it. If you cache this, then the second time you get to this point, it's much faster. And in your input, you have lots of these branchings that go in different directions and then return to the same point. So the cache will be very useful. As you can see, part 2 is still running, so I'll stop it. I'll go ahead and from functools, I'll import cache, and I will add a cache to my count paths. And now I'll run part 2 again. And it's done. It was essentially instantaneous. The result is 332 something something 990. Let's see, 332 something something 990. So there you go. It's 12 past 5. I started the stream 11 minutes ago and part 2 is already solved. Now, don't be fooled. I mean, I've seen lots of people online and friends that did this correctly and efficiently the first time around. I'll be honest with you, what I did when I was solving this problem was everything as you see on the screen except the cache. I didn't add the cache. And when I saw it was taking too long, my mind immediately went for a more involved solution that worked, but with way too much code when compared to just adding the cache decorator. And the thing that I missed, which made me forget I could use the cache, is thinking about the divergences, which then turn into convergences. When you have branching like this, caching is typically a good idea. Alright, questions about the code? If there are no questions, then I think the obvious next step is going for day 9 part 2, which I haven't finished yet. I was hoping I would get time to solve it in one of the streams, and here we are. So that's what I'm thinking of doing. If you already solved part 2 of day 9, or if you couldn't care less, then thank you very much for joining the stream. I will be back tomorrow at 5 p.m. UTC to solve day 12, which is the last day. Otherwise, if you care about part 9, if you're interested in seeing what I end up doing or something else, then just stick around, because that's what I will be doing now. Alrighty, so in that case, let's go to day 9. And let's see if we can solve part 2 here. Now, where were we? Yeah, what a mess. Alright, so for part 2, just a quick reminder or a refresher. I think I actually have the diagram here. Do I? Yes, exactly. So for part 2, we have a region that's delimited we have a closed region that's delimited by the input. The input gives us the vertices, and then we can consider the segments that connect consecutive points. And what we need to do is find the largest rectangle that has opposite corners in those vertices, in those points, but that's fully contained inside the region. For example, the rectangle in blue does not work because there's a big section that's outside of the region. Whereas the rectangle in green that I'm drawing now could work. I'm not entirely sure it's the largest, but could work. Well, strictly speaking, it couldn't work because it needs one of the corners needs to be a given point. So maybe, for example, this one would work because it's fully inside the region. So that's what we need to solve. Now there's a lot of points, so we were trying to do this efficiently. We're doing coordinate compression. So we only grab the points that are relevant and we ignore all rows or columns that don't have anything in them, and we compress the coordinates. So the shape, the red shape on the right becomes the red shape on the left in the compressed space. This is irrelevant for now. In the compressed space. So that's what we already have. The code already compresses. Now what I need is a point that's in the interior of my region, because I want to do flood filling to find all points that are inside my region. But as it turns out, it's kind of annoying to get the points here. So what I'll do is I'll cheat. I mean, it's not cheating, it's just, it feels weird. I'll do flood filling on the half coordinate points. So the corner at the top left is 2, 3, the corner at the top right is 3, 3. And instead of thinking about the points with integer coordinates, I'll do the flood filling in points that are 0.5, 0.5. That will allow me to find all points marked in blue. And then when I move them back to the top left, I will be left with the points inside the region. So that's the plan for now, is to do this flood filling on the half coordinates. And the only thing I need to be careful of is when I'm flood filling and checking the neighbors, I need to check if by looking at the neighbor, I crossed an edge. Because if I cross an edge, I know that this point is outside and I don't want to include it. All right, any questions, or am I good to go? All right, let's see. Feel free to share your questions as they pop up, but for now I'll keep going. So this is the compressed points, the edges, computing the edges. I don't need this. Actually, this might be helpful. Let's leave it there. This was the part that was not working. Oh, right. Yeah, but now we can use it as a, what is it? Topmost and leftmost. Right, so now we can use this as a source for the first half coordinate point. So how do we do that? We find all topmost points, all of them, and then we pick the one that's to the left. So we're going to sort by largest y and then smallest x. So this is the top leftmost point. Top leftmost point. I think this is correct. Let's just double check because I don't want to make a mistake here and then spend hours figuring this out. So edges equals, say, a point that's here and then another one that's a bit to the right, and then a couple of points that are under. And let's do 0 or -1, 9 as well. All right, and now that piece of code, this should return the point 0, 10, because it's the topmost point that's on the left. All right, looks about right. So we have the top leftmost point, which means that the start is going to be the half point that's slightly to the right and slightly down. This is our starting point. And now we're going to flood fill the interior region. And the inside is, this starts on the inside already. Great. Now we have a point that's inside, and now we need to go through its neighbors. And this is another half point, so the thing we need to make sure is that the half, the full point that's in between, so the half change, so x plus 0.5 dx and y plus 0.5 dy, we need to make sure that this is not an edge. So let's round this. Let's also round this. All right, and now we check if we just crossed an edge. So if the half change is an edge, means we're crossing. So we're doing the red arrow, sorry, the orange arrow is dx dy. By doing 0.5, we're checking this point here. Wait, actually, I need to be careful. Right, because what I'm doing is by doing 0.5, I'm grabbing these points and I need to compare with the point that's right on the top left, of course. Okay. So what I was doing is I need to check if I'm crossing an edge, right? And what I have about the edges are the points that make up the edges. So the best way to check if I'm crossing an edge is to take a look at the result I get to the point I get to, and look on the top left. Because when I started working with the half points, I moved everything a bit to the down, a bit down and a bit to the right. So I can compare with the top left. I think that's the case. Let me double check when I do this. No, I'm saying this wrong. How do I check if this is an edge? If I'm going up, I do half and left. If I'm going down, okay, got it. All right. So because I'm working with half points, if I'm crossing an edge, regardless of the direction in which I'm going, I will have 2 points perpendicular to the direction in which I was going. So for example, in this point, if I'm going right, if I'm crossing an edge, it means that I have the 2 points in the direction that's perpendicular to my arrow. So whenever I go left or right, I need to cut the arrow in half and then look at one of the points above or below. And if I'm going up or down, I cut the arrow in half and I'll check either left or right. Okay, because I need to look in the perpendicular direction to the arrow. Great, so given an arrow, so this is wrong, and this needs to be fixed. So let's go to the neighbors. Where are they? And now we do the edge check. So based on the arrows, we can figure out, or we can map the arrows to the offsets where we can check for an edge. So 0, 1, what is 0, 1? 0, 1 is going up. So if we go up, and we are in this point, one point we can use to check for an edge is this one. So that's going to be minus 0.5 on x, minus 0.5, and plus 0.5 on y. So that's minus 0.5 plus 0.5. And if we go down, the x can also be minus 0.5, but the y needs to be minus. So the sign of the second one flips. So that's minus. And now we do a similar thing for going left and right. So 1, 0 is going right. If we go right, we add 0.5 to x to get here, and then we can look up. That works. So we add 0.5. And then we can look up, it doesn't make a difference. And so when we go left, the sign of the x flips. All right, so that gives us the edge check. Right, so now the edge x, or edge dx and edge dy come from the edge check. Okay. And now the possible edge points are x plus ex, y plus ey, and now we check if this point is an edge or not, because if it is, we're crossing outside, we skip, or if the new point has already been tracked. If it hasn't, then we queue these points to be tracked next, and we also set it to be inside. Now this is a bit redundant. It looks like my inside and my tracked are exactly the same, so we can get rid of this. Great. And now when I'm done, I've finished flood filling. So the flood fill is finished. Now what I need to do is take all of my points, which are in half coordinates, and move them back to the original space. So I did plus minus, so now I gotta undo that. I need to do minus plus. All right, so let's see. The interior is every single point that was tracked minus those coordinates minus the original offsets. So minus 0.5 plus 0.5, minus 0.5 plus 0.5 for x, y in tracked. And then from this we subtract points that also belong to the edges, because if I zoom out here and if I get rid of these orange arrows, just bear with me for a second. All right, when I work with the half points, some of these points, when they go back, they end up, it turns out that they were the edges, so we just get rid of those, so that in the end I have only the points that are in the interior, which are, in this case, well, in this hand-drawn case, just this one, the one in the center, which comes from here. All right, this was a lot of work. Let's see if this is working. Let me double check. The flood fill finished, and then let's print the length of the interior. Now I'm working with my sample. Okay, we can work with the sample first. UV run solution.py. Topmost point is not defined because I changed its name. Now edge check key error 2.5 3.5. Because the edge check is supposed to take the arrow as the key, not the point you're the dx and dy, not the new. Alright, we're getting closer, but I still have stupid mistakes. Okay, flood fill finished, and I found nothing inside, which is not great. Isn't my sample, what's my sample like? Let me open day 9. I think I should have a 1 point in the interior. 1, 2, 3, 4, 5, 6, 7, 8. Exactly. So this is my sample input. This is my sample input. And if I do the compression by hand, I get rid of this row. I get rid of this row. And now I get rid of these 4 columns. Alright, now there's still a column here that has nothing, which is this one, so I can get rid of it. Now this is also an empty row, so I can get rid of it. And I have one final empty column, which is this one, so I can delete it as well. Alright. Isn't this what I had drawn in the other? Where's the other? Okay. If I connect everything, I'll end up with this region, which has a single interior point. So why am I not finding it in my flood fill? Minus the edges. This is a bit upsetting. Minus plus. Let me also print the compressed coordinates to see if my drawing is correct. Now let's open Excalidraw and the coordinates I get. I'm trying to put them side by side, but I'm struggling. Okay, let's do left half, right half. So 1, 0 is what? 1 is x, 0 is y. By the way, are they doing... How are their coordinates? 7, 1. 1, 2, 3, 4, 5, 6, 7, 1. Oh no, so they're doing it from the top as well. Alright. So maybe I want to keep sure. Maybe I want to make sure I have the y in the same direction, which is here. So this is slightly to the right. And this is the largest y. So the topmost will have the smallest y. So the smallest y is at the top. If this is the smallest, then I need to increment it by a little bit to make sure I'm in the interior. And then I subtract. And then the edge checks are also wrong. So 0, 1 points down. 0, 1 is pointing down. No, I think this is correct. Okay. Let's run this again. Ah, finally. Okay, we got 1 point inside. Damn. And it should be the 1 point inside should be this one, which is going to be 0, 1, 2. It's going to be the point 2, 1, hopefully. Let's see. Let's print the interior point. Two, 1. Is it? Did I get it right? 2, 1. Okay, finally. All right. We're back on track. Now let's make these integers. I'm rounding instead of using int, because int will grab the integer part, and if there's an annoying rounding error, I might go from something that looks like 5.0 to 4, which is not what I want. So by rounding, even if I get 499999999, it rounds to 5. All right. Okay, the interior is good, finally. So now that we have the interior and the edges, the full region is given by the edges and the interior. If a point is an edge or in the interior, it's part of the full region. And now what we do is we go through all possible rectangles, just like part 1. Where is part 1? Part 1. We go through all possible rectangles, and then we check. So we maybe start with the largest. Yeah, we start with the largest rectangle. I'm thinking, does it make a difference? No, we just go through the rectangles, we check their size, and if it's the largest we found so far, we check if it's fully contained within the region. And if it is, we update the largest found so far. Great. How do we do this? So first we need to go through all points with combinations, just like the original part 1 loop. Let me grab this as well. So we go through all possible rectangles and we compute the area. Now, if this area is smaller than or equal to the largest area so far, we don't care about this rectangle, we just skip. If not, we need to compress this rectangle, we need to move it to the compressed coordinates, because then we're going to check if the rectangle is fully within the region. So we compress CAX and CAY. How did the compressing go? Let's see, compressed points. Oh, I have a function compress, very convenient. Where is the function compress? Ah, it's here, okay. So now we compress points A and B. AX, AY. BAX, compressed. We compress the 2 points. Now we generate the interior of this rectangle along with the edges. Actually, it's enough to compress the edges to generate all points along the edges. So that's going to be from CAX, CAY. All right, let me make a quick drawing. So what's happening? Let's maximize this. We are in our full input space. Do I have a diagram for that? Kinda. We are in our full input. We're going to pick 2 random points, like this one and this one. And we're going to think of the rectangle that's defined by them. And we check. If it's a large rectangle, what we do is we convert it into the compressed coordinates here to this world. And now suppose that after compressing the rectangle is this one. What we're doing is we have the 2 opposite corners. What I'll do is I'll generate all points along the edges. And I will check if all of the points along the edges are inside the region. Because if they are not, and we can see that a couple of them are not, if they are not, then the rectangle is not inside the region. So now, given the opposite corners, I have to generate the points along the edges. I can finally see light at the end of the tunnel. Finally. Alright, how do we do this? So this is not interior, this is rectangle edges. That's going to be, let's do this first from the top left corner to the top right corner. So we're going to go from here to CBX. Alright, so it's going to be X, CAY for X in range. Now I'm thinking I might want to swap the orders. No, we can just do minimum of CAX, CBX up to the maximum plus 1 because it's inclusive. So this is one of the edges. Now we just need to do the same thing for the remaining 3. So this is either the top or the bottom edge. We don't know for sure because of CAY, but CBY is going to be the other one. So if this is the top edge, this is the bottom one. And now we do a similar thing for the left. So first we change this to be this, and this becomes a Y, and this becomes a Y, and this becomes a Y, and so does this. And now if this is the left edge, then the right edge is obtained by doing CBX. These give me all of my rectangle edges, and now if all of these points are inside the full region, then I can update my rectangle. Now what is it that I need to save? Is my puzzle asking for the area, or is it asking for coordinates? Or yeah, the largest area. I'm very nervous because I think this is supposed to be it, but I'm not sure it's gonna work because I've spent so much time with this problem already. Alright everyone, wish me luck. Let's run this UV run solution.py. It's not gonna work because it's the sample input. So actually, yeah, that's clever. Let's maybe check first that it runs for the sample input. It finds a 24. Is that the correct answer for the sample? Let's see. 24. Great. So now let's swap in the sample input for the full input. Let's run this. Flood fill finished. Now it's checking the areas and it found this rectangle. It took a couple of seconds. Not terribly slow, but also not as quick as some other solutions. We did it. I can retire now. You have no idea how relieved I am. Finally. Are there better solutions? Yes, I'm sure there are. But this is what I came up with. Let's see. What time is it? You know what? We still have 15 minutes. Let's just take a look at let's maybe visualize the input. How does that sound? Because the input has a funny shape. And I did not leverage that information here. But yeah. Okay, is the solution very efficient? It really isn't. We're spending a lot of time computing the full region, flood filling the region, and then checking all of the areas. I think, from what I read, the most efficient way of tackling this would be with ray casting. It's a very nice technique from computational geometry, which I have not mastered yet. Alright folks, I appreciate your applause in the chat. You have no idea how relieved I am. So now let's do a quick Pygame visualization here, just to draw all of the points on the screen, so you can see what the input shape is like. So let me add Pygame to my script. All right. Now I want to grab my input. I want to grab my input.txt, and now I'll find the smallest x. Min x is the minimum for x in. I don't want to return, I want the points, in points. And the max x is going to be max of x for x something in points. And now I'll do the same thing for y. Y. All right. So now I know how big the input is in terms of coordinates. What I'll do next is create a screen that goes from 0 to max x plus min x. I know this is kind of weird, but suppose that the minimum x is 100. I want to start my coordinates at 0. So there's going to be a margin of 100 pixels on the left. So to make the margin on the right equally big, I just add the minimum to the width. And I do the same thing for the height. Max y plus min y. Now I'm going to create a huge... Actually, I don't want to show this on the screen because this is going to be almost 100,000 pixels. I just want to draw the image and then open it. So I'm not going to create a screen, I'm going to create a surface. How do I do that with Pygame? Pygame.org/docs. I have a surface here, surface. Surface width height, okay. What was it? Pygame.surface width height. And now I want to go through each pair of consecutive points and I want to draw a line on this surface. So there was a piece of code that allowed me to do this. So I'm going to need chain and pairwise. All right, so from iter tools, import the chain and the pairwise. The full chain, these are all of my points. Now for from start and in pairwise of my full chain. So these are this is every pair of points that creates a segment. So now I need to draw a line. So pygame.draw line from actually on the surface from the start to the end. And now I need to see the rest of the arguments. So I'm drawing a line. Surface, actually color first and then the positions. So color, let's fill the surface with white and let's draw this in black. 0. And then we take the surface and we save it. So pygame dot, I think it's image dot something to save the image. Pygame dot image dot save. Image.save this surface as region.png. Now we run this. Please don't use Pygame as an image manipulation library, but I'm not fluent with anything else. How come Pygame is not defined? Because I forgot to import it. Python 101, import the libraries you want to use. Otherwise the code doesn't work. Now you give it a second. Maybe I have a... Oh no, it was still opening Pygame. I thought it was already running. Now you give it a second to draw all of the points. And I wonder if having an image that's 100,000 pixels long is maybe too much for my computer. Let's see if this finishes in a reasonable amount of time. Otherwise I'll maybe compress the... Oh, it finished. Let's see if I can open this image. What did I call it? I called it... Wait, what did I call the image file? Region.png. Is this not here? I'm confused. Where did my image go? Did I not do the file name? It should have saved the... Let me use my Finder. Documents, AOC, 2025, day 9. Could it be that it's still somehow writing because it was so huge? Okay, in that case, we'll do the following. We will again cheat because we are cheaters here. I wonder if actually compressing might be a good idea. So compressing is going to deform it a little bit, but it might still look good. Let's see if we can do this. So we read the input. Now we compress. We start by compressing. Let's see. The axes are these. These are the compressed, compressed, compressed. Now we do everything for the compressed points. And now we try again. Oh, right. And the problem is, again, I can't save images in Pygame with Python 3.14 yet. So I need to run this with Python 3.12. Saving images of extended formats. What do you mean? Did I not run this with Python 3.12? No, I did not. UV run Python 3.12 vis.py. Okay, now it's Python 3.12. We give it a second to start Pygame. Then we give it a second to run the image, to build the image, to draw the image. And it's done. Now let's open the region. There you go. That's neat. Oops, wrong thing. So this is already compressed, so it's deformed. It's a bit deformed. So it's not the original shape, the exact original shape, but you can see that there's clearly, like, we know where the largest rectangle is going to be. It's either going to be at the top and hitting this line over here, or it's going to be at the bottom but hitting the line the same way. Now let me close. I think the problem was a Python version problem, so let's try the huge image again with Python 3.12. We give it a second to create the image. And now we open the region.png. Nope. This is the old one. Maybe it's just such a large image that I can't save it. Okay, let's do the following. I'll do everything with points that are 10 times smaller. So I'm preserving the ratio of the lengths, but I'm making everything shorter. Sorry, this is not what I want. I want to run the visualization. Now we open the region. There you go. It's very, but it's very, very faint. I doubt you'll be able to see it. Maybe if I zoom in, you can see the lines. Yeah, like if I zoom in a lot, you can start seeing the lines. Because the scale of the region to the width of the lines is very, very small. How do I zoom out? So that's why you can barely see anything in the stream. Like I doubt you can see anything at all. How can I fix this for you? I can make the line wider. Let's do width equals 10 maybe. So 10 times thicker. So we run this and then we open the image. All right, now it's much more visible. Yeah, there you go. This is the input for day 9. So you can see there's like this shape. This didn't happen on purpose. This is not a random shape. This was handpicked by the creator of Advent of Code. Pretty interesting. And again, it's highly likely that the largest rectangle lives here. Either here or under it. So depending on whether you consider this cheating or not, but you could say, well, fix these 2 points, well, one first and then the other, but fix one of those points and then look for points around here to create rectangles with them. And some of these will generate rectangles that are outside, fine, but the others will generate rectangles inside. So really this would be O of n along the points, because you go through the first half for one of the corners and the other half for the other corner, and the solution lives there somewhere. It's never going to be points from opposite halves, because that's going to cross this region, and it's never 2 points in the same half, because you will always go out. Oops. Yeah, very interesting stuff. Alright everyone, let me save this. Let's save all of this. Finish day 9, and then let's add an emoji here, because why not? And now we push. Very well. I'll put the link in the chat. And I think we will call it a day, folks. We're done for today. This was pretty cool. We solved, at least for me, I mean, finally solved day 9 completely. Not the most efficient solution ever, but at least it's working. So day 9 is done. Day 11 was done on stream in the first maybe 15 minutes or so. And tomorrow we'll be back again at 5 PM UTC to solve day 12, the final day of Advent of Code. Thank you very much everyone for watching, and I'll see you tomorrow. Bye.